Okay, thanks for that, Eric. I guess what I want to talk about, really, to just in a certain way complement the presentation we've just seen, is technology disruption. And the reason for it really is that Velocidata is disruption of an unusual kind. It is disruptive in the sense that it goes much faster than what preceded it, but it's disruptive. This should become clear in what I present how disruptive it is. And that begs a lot of questions, in actual fact. So, first of all, this is a curved, this is a graphic that I've put up several times before, but for those that haven't seen it before, I'll just go through this as fast as I can. We are on the vertical scale here. We're looking at response times, but the response time, it's a logarithmic scale, so the first at the bottom is between 100th and 1/10th of a second, then between a tenth and 1 second, and 1 and 10 seconds, and then so on and so forth, you know. So if this was actually a linear scale, it would be like 2 miles in the sky. And the only way you can actually make sense of a graph like this is to use a logarithmic scale. On a horizontal scale, we're looking at workload complexity, really. There is no absolute measure because workload can be pinned down by I/O, it could be pinned down by memory contention, it can be pinned down by maxing out on the CPU processor. But in the general sense, you know, you could imagine there being a server, and in one way or another you can clog up the server. So the bigger the workload, the more of any given unit of server it actually consumes. So that's the horizontal axis. And what I've drawn here is the various curves that come down here is starting in 1960. This is a rough estimate of what was achievable on the early IBM mainframes. You really couldn't do anything in particularly fast, and you were looking at what I color banded here as medium batch to slow batch as what was possible, and not much of that was possible. The next curve at 1970 has us moving down to response time that gets just outside the transactional range, and you get fast batch applications as well as medium batch and slow batch applications. By 1980, we're in the transactional world. All of a sudden, we're actually processing transactions online, on terminals, random arrival transactions to what was in those days pretty much always the mainframe, and getting response times somewhere below the 10 second, but towards 1 second. In those days, that was regarded as extraordinarily fast. By 1990, we've got into the PC world, and the PC is giving us interactive interaction with the PC itself, you know, which is the screen, the GUI. And in order to do that, it has to respond pretty much at 1/10th of a second. That is, if you move the mouse and the mouse pointer has to go at that speed after a movement of the mouse. Otherwise, it will appear to be slow and unusable. So, you know, that's the kind of PC era that hit us by about 1990, and the user interface took off from there. By about year 2000, we're actually moving into real-time applications at the lower end. Obviously, it had to be a small workload to be real-time, but we've gone below human time, and we're now program to program time. And by 2010, we're simply moving out now from these extremely low latencies, and larger workloads can operate at lower and lower latencies. Now, what happens, these are the white arrows here on the graph, what actually happens is that as these latencies move in, applications start migrating from being slow batch to medium batch to fast batch, transactional to interactive to real time. And the effect of this is it's actually incredibly disruptive, because you get an old application in one way or another was built for a particular kind of response time. A new application is built by some other vendor that goes an order of magnitude faster, you know, at least 10 times faster, and it actually changes the application. And you can see that happening right now in the world of BI, where applications that we know, analytical applications that used to take days or hours, are coming down to hours and minutes. And that's kind of changing everything. Below the, I mean, I drew this particular graph in about 2011. Years have gone by, but the The blank area beneath this final curve here is the area of as yet unrealized applications. Now, what was happening when I drew this graph, and what was pretty predictable, was that you get an order of magnitude improvement in speed roughly every 6 years, and that was due to Moore's law. And Moore's law was happening not just on the chips, it was happening on the switches, it was happening in memory, it was happening on network speeds, and so on and so forth. It rippled all the way through. It wasn't so good on disk. This wasn't increasing at the same kind of rate. But the general sense was, certainly let 6 years go by, you've got an order of magnitude improvement, and quite likely existing established applications will start to be disruptive by new innovative applications. Something very odd happened around about 2011, 2012. Because this is a curve of disruption. But what we started to get was disruption over disruption. And I'm no longer, you could draw this graph and have a certain expectation of what might occur in the year 2020, but I'm not so certain that that pattern holds anymore. I think that in actual fact the acceleration itself has gone up. And the reason it's gone up is, well, I mean, the evidence that it's gone up is I'm now encountering, and it's not just velocity. Velocity is a very interesting technology to me, but there are other technologies that I'm running into. They're getting order of magnitudes of 100 over existing, and even 1,000 over existing capabilities. And that indicates that in one way or another, it's not just Moore's law that's in play anymore, and what appears to be in play is parallelism. In other words, Moore's law allowed us to scale up, and that allowed us to have this incredibly disruptive pattern in the whole of the world of computer applications. But now the technology has allowed us to scale out, not just scale out across multiple servers, but scale out on individual motherboards, scale out at various levels. We've scaled out on the CPU itself. It's used to in 2004 have a single processor, and now you can get them with 16 processors, even more in actual fact. You can get multiple extraordinary number of processors. So what I think has actually happened is that parallelism has increased the potential rate of disruption. And that's very interesting from the user perspective, because there's certain technologies coming in that are just way ahead of what went before in terms of speed. And maybe that creates opportunities, and of course it only creates an opportunity for you if you actually have a need for the particular speed that it delivers. The thing that actually becomes obvious to me is it's like the parallelism we could have been doing this 30 years ago. It was possible. In fact, we were doing it in high-performance computing with Cray machines that were built to be parallel. But parallelism didn't infest the whole of computing, and now it has done. And it has done so simply because the commodity chips are now multi-core, and multi-core with large numbers of cores, and that just fundamentally makes it necessary to write parallel software. And then the logical conclusion of that was, well, parallel software will become the norm. It is pretty much always faster. Very few pieces of software which you cannot improve in speed by parallelism, and certainly some activities can be improved in speed quite dramatically with parallelism. This isn't really just about software. In fact, Velocidate is a very good example of what's been built here. It's been built up from the ground up on hardware, making use of hardware capabilities, but embodies software, because, you can't run an application without having somebody coding something. Parallelism is going to affect, in my opinion, it's going to affect all software. It'll probably take about 10 years, but there'll be things where there's a big advantage to go parallel, things where there's a lesser advantage, and obviously the low-hanging fruit will get picked first. But in my opinion, everything will execute in parallel in time. And that means everything will go much faster. And this is the disruption thing. It's worth mentioning here the CPU, GPU, FPGA, specifically because this is what Velocidata does. And therefore, it's just worth mentioning that these chips are actually kind of commodity chips in the sense that, you don't actually have to specially design them and specially fabricate them in order to build devices that use them. You can actually get them off the shelf fairly cheap. put as many as you want on a board. But actually making an application work on the board is a bit, it's not a trivial thing, but the idea would be that you could build an appliance that was particularly focused on a given level of, a given kind of application, and this is what Velocidata's done. And this, actually, a CPU, at the moment, you're probably pushed to get more than about 16 cores in a CPU and a GPU. You can get hundreds of cores. On FPGAs are actually, what they do is they embed software logic onto a chip, so the software never needs to be loaded. You just drive the data through the chip, and that's what makes it execute extraordinarily fast. But it's not a trivial thing to put a CPU and a GPU and an FPGA together and make it run an application. So that's, in a sense, that's part of the conversation that one needs to have with Velocidata as to how they did it, what the limitations are, and what the advantages are. And the use of these chips, without a shadow of a doubt, can create acceleration above 100x. I don't think any of the claims that Velocidata is making are in any way unbelievable. When you actually look at the technology, they're entirely believable, and of course they've got customers to prove it. And this is the other thing that goes on. There's a memory cascade. It isn't just that you can, in one way or another, use a lot of parallel cores, but you also got the fact that there's a big difference between disk or SSD and RAM and the memory that's actually on chip. And on an Intel chip, level 1 cache is actually 100 times faster than memory. Level 2 cache about 30 times faster, and level 3 cache is just under 10 times faster. So if you can drag the data onto the CPU, and this applies to GPUs as well, but if you can drag the data on and do a lot of the processing without actually going back to memory, you can get dramatic speeds. You can get 100x simply by writing the software in such a way that it can do that, always presuming it's an application where there's enough level 1, 2, and 3 cache to be able to do that. But you look at an Intel chip, now you're looking at 32K of level 1 cache. That's not small. Level 2 cache, you're actually at a quarter of a meg, and level 3 cache is like a PC used to be not so long ago. So there's an extraordinary amount of resource there for processing stuff extremely fast. The upshot of this really is, going forward, the old limitations that we thought of in terms of response times are no longer so limiting.